My name is Fadil, and I'm an intern working at S2P Africa. And today I'll be presenting our work on the parametric design and testing of Pounded Yam blades. So, Pounded Yam is a popular West African staple, normally eaten or complemented with soups, and is a very delicious meat by my heart. And traditionally, it is made by pounding yam into a thick, consistent paste. We use the mortar and pestle to do that. But now there are modern machines that actually do the work. So we have pounded yam machines that pound yam very well. But this only pound yam. People over time have realized that you could use food processors to pound yam, but therein lies the problem. The blades for food processors are generally designed to slice and dice yam. They don't really pound the yam properly. So what you end up having is a lumpy mash of food. And locally made machines, they actually do pound the yam very well, but they're usually expensive and they're usually over-designed. So we wanted to exploit this. What do we want to do? We want to design a set of blades that will properly pound the yam. How do we hope to achieve this? We'll be creating a 3D model of existing blades. We're going to carry out static stress simulations to see which parts of these blades are most likely to fail. We'll create new models based on that result. We're going to print these blades and we're going to test them. So we're going to be comparing the texture of these blades and how well they pound. The pounded yam assembly consists of 3 parts: the blades, as you can see here, number 1, the overhead cap, and the motor mount. So these 3 components are joined together and they are put into the food processor on the right. So what we're going to do is we want to reverse engineer all of these components so that we can 3D print them and make tweaks to the design. So here we have the model, that is the motor mount and the overhead cap. These were designed using Fusion 360, and you can see a section through the model. Now, the important aspect of this, which is the blades. What influenced our design decisions were basically the pounded yam blades for the machines and the food processor blades. The food processor blades didn't pound properly, but the pounded yam blades, they pounded properly, but they just over-designed and heavy. So basically, we brought the best of 2 worlds together. We moved from a slimmer profile to a much more chunkier, thicker profile that does the work of pounding better. So this is how we progressed throughout the design phase. But when we did this, we ran into a problem: stress. So we applied 200 newtons, an arbitrary force, to our parts, and we realized that our new design had an increase in stress by about 60%. This basically meant under the same conditions, our design was most likely to fail, and that was not good. So as you can see here, the red regions are regions of high stress concentrations, and we really want to avoid that. So in order to redistribute the loads in those regions, we added fillets. So these fillets actually help strengthen sharp corners and avoid shear tear-outs in general. And when we refined our geometry and we tried to add fillets, we're able to reduce the stress actually from the original by about 56%. So these new blades are actually stronger than the original, while still giving us the ability to be able to pound yam better because of its beefier features. Now, permit me to go into a little bit of continuum mechanics here. The reason why we're going to be explaining this is so that we can understand why the von Mises stress is important for us in our simulation. In most simulation software, specifically Autodesk, they use the von Mises stress, and this is because in order to define stress, you actually need 9 components, and all of these components are tensors. So you need to be able to define, you need to be able to compare an apples-to-apples comparison. We can't necessarily compare a tensor with a scalar, and in this case, our scalar is the yield strength. So what the von Mises stress allows us to do is allows us to find an equivalent magnitude, basically a representation of all of these components, these tensors, into a scalar value, that is our invariant of the stress tensor, that can use to do an apples-to-apples comparison. So that's why the von Mises stress is very important. So I don't want to go too in-depth into the continuum mechanics side of this, but if you are interested in learning about tensors, stresses, and strains, you could actually go to our website here, where we offer extensive studies on continuum mechanics. I think it would be nice if you actually looked at it because there are some wonderful lectures there. For the prototyping, after we had defined our design, we imported them into the slicer software. And here in the slicer software, we can tweak various parameters of our model. We can increase the number of layers, we can increase the infill, and all those kind of things. And what it does is the slicer converts the 3D CAD file into G code. G code is a set of instructions that the 3D printer can carry out. Now, at this point, it is important to note that 3D printed parts are generally weak along the z-axis. We did not anticipate for this at first because in our simulation, we couldn't see. Our simulations are carried out as if the whole model is solid. But when we design them, they're going to be in layers. So there's a chance for us to have a torque failure because these parts are going to be rotating. So when we saw this, we added more walls and more shells in the design so that we can compensate for this failure. Now, I love talking about hardware, so I have to put this here. For those that are curious about the hardware we use to prototype, we use the KDX Mass and the X Plus printers for 3D printing. These are both direct drive printers that we have over at the lab. So here we have some of the printed components. It turns out that 2.5 mm in your design isn't entirely 2.5 mm when you print it out. There's always that slight tolerance that you have to deal with. So at first instance, when we printed the blades out, they didn't really fit properly. Some parts were too big, some parts were too small. I guess that's something you have to go through when you're prototyping. So we made several tests until we got the blades that actually fitted well together. These are just samples of what we designed. Now, disclaimer, we're not cooks, we're engineers, but we did manage to be able to get yam from the market. We cut them into small chunks and then we bought them. So at the top right, you can see our own design, and at the top left, you can see the original blades. Below that, you can see the original blade and all the other blades that were printed for. So I'm going to play a video now, so you guys can see the results we got from our testing. Oh, okay. So these are yam. These are our setup. This is the yam when we after cooking it. This is the yam in the food processor, and this is after we've pounded it. Okay.
Good day. This is our first test. We're testing our yam pounder blades. Well, for the first test, we have the original blades that came with the yam pounding machine. Notice that these blades are black, and this will be our test, our control test, our control experiment. Okay, so we're about to start the second test. These blades were designed to fail, at least according to the static stress simulation, under a force of 200 newtons. So we want to see if the yam that we've boiled actually can exert that much amount of force on these blades. This is the results of our second test. We can see the performance of these blades, not as neat as the first test. We'll move over to testing the third blade. Our test 3, we're going to be looking at this set of blades. They have thin blades compared to the blades used for the second test. I want to see how well they can pound the yam using the blender. Testing these blades, what we noticed was that a lot of the yam fell under the blade and into this middle space that we have here, central space. So we can say that the blades didn't perform as we needed them to, and you can see that some of the yam also stained the machine. So the blades did not perform as we wanted them to, as we would have loved them to. So we're going to move on to test 4 now. For our fourth and final test, we'll be testing these blades, which are thick. They have a fillet around here, and we can also see that one blade is longer than the other. Using this video as a reference, the blade on the left is longer than the blade on the right. So we're going to fit that in and put in the yam for pounding. On our fourth test, we can see this very excellent result. We can see that the yam is uniform in texture on all sides. We can see that it's a very good blend, ready to eat. Experiments done, we can see that these blades, the blades from our fourth test, performed the best and gave the smoothest texture of pounded yam. These blades take the day.
So this is our optimal blades. These were our best performing blades. We gave the most consistent texture. And during the test, we observed that the coupling mechanism that came in the original design wasn't good enough. While we were pounding, the blades tend to leave the motor mount and move up. But we've already fixed this in our present design. We made a better coupling mechanism, but we just haven't tested it out. Thank you for listening.